Welcome back for another lesson in Math 8. Today we're in Unit 4, Lesson 3, more with balanced moves and more work with rewriting equations using the same solutions, or keeping the same solutions. Going to be using the hangers again a little bit more. For this first part, we have figures A, B, C, and D show the result of simplifying the hanger in figure A by removing equal weights from each side. Here are our different hangers. Notice that we get a little bit larger to smaller. And then here's some equations to be able to work with. So we're looking at an equation or equations, and we're supposed to, each equation represents one of the larger hangers up here in the diagram. Something that we can look at in these diagrams is we can look for patterns that we notice. Let's start with letter A, and let's look for a pattern and some things that we may notice. And we see that there's a square and 3 triangles, and a square and 3 triangles, and then 2 circles. Over here, don't see the same pattern, but then we go to the next hanger and we see that square, triangle, triangle, triangle again twice. And then we see it again in the third one in C, and then we don't see it again in D. These patterns can help us when we know the values of the shapes. So we're going to go ahead and look down here with these ones, and we're going to see some equations, and we're going to see which of these would represent one of those hangers or one of those diagrams. Now, as I talked about, we talked about that square, triangles, triangles, triangle, those 3 of them, and I get to match that up with something. When I see this pattern happening twice, right here and right here, that helps me to understand that there's 2 of something going on, or 2 groups that I can look for. When we look into the equations and we see them written with numbers and letters, we're actually talking about looking for things like parentheses. Now, parentheses are a grouping symbol, and so that grouping symbol helps us to work through what's called the distributive property, where we say we have 2 of a group of x plus 3y. Now, in this case, I need to be able to distinguish between the 2 of them because I have 2 different groups like that. 2 times the sum of x and 3y is just what we have on that one side of the hanger. So this would be the only thing on the left. This can't be figure A because there's more to it. There's these 2 circles. So this one must be figure B. I can continue to make sure that that's really figure B. What I've concluded is that the square is going to be an x, and each of these triangles will be a y. And that helps me on the other side to be able to look at this and say, okay, x, 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 y, y. And then all of the other figures, all the other hangers, I would see the same thing. But that leaves me with something different when I look at figure A, where I have a couple circles. So let's go ahead and look at figure A and see how that one's a little different. I have 2 of the same groupings as I saw in B. I have x plus 3 times y and another x plus 3 times y. So I have 2 of these groupings. So I have the sum of x and 3y twice plus 2z. By matching this with this expression, or with this term in this expression, I understand that each of these circles represent a z. And so now I know that I have 2z plus 4x's right here and 2 y's. And I can confirm that this equation right here is letter A. Letter C takes us to an x plus y 3 times. So we have x plus 3y is equal to 2 x's and 1 y. So 2 times x plus y. This one would be C. And then we see D is pretty simple. This is just 2 times y, and then the box would be x. So this is letter D. Now let's look at the progress of that as we write which expression goes to which figure. Unfortunately, this travels on to the next page. So we're just going to go ahead and put it all right here, C and D, so you can see all of it together. We started out with A, which was twice the value of the sum of x and 3y is equal to 2 times z, plus 2 times z is equal to 2 times z plus 4 times x plus 2 times y. The next expression, simplifying from A to B, what we see differently here is we see that the z's are now gone. So we eliminated those z's. So we have twice the value of the sum of x and 3y is equal to 4 times x plus 2y. We eliminated these two z's through subtraction because this one is positive and this one is also positive, and by subtracting the 2z from the expression on the left, we've eliminated it, also eliminating the 2z on the right. We've taken an equal portion from both hangers, maintaining that balance. In letter C, we can look at what has been removed. Well, from C, what we can see on this one over here is we can see something just a little bit different. Let's go ahead and write it so we can see what it looks like. We have x plus 3 times y is equal to 2 times x plus y. Now, if we look at what has been removed here, we start looking at the triangles and the squares, and we see that on letter C, we only have one triangle left. That tells us that one of the y's had been eliminated, but also, excuse me, more than that. If we look at the expression here on the left, we see that one of these full sets has been eliminated. Now, how is that happening? Well, we can look at that and we can see that these values here on the right side have actually taken on a larger value. We see that through distributive property, which means that this expression right here, 2 times the sum of x and 3y, actually represents a larger value, which is twice the value of x plus 6 times the value of y. If we look at all of them together, we have x and x, 2 x's, and 3y and 6 y's. And then when we start eliminating on these pieces, by eliminating that whole factor there, we also eliminated some of the pieces from the right side. Excuse me. So if we look a little bit closer, there's another way to do this. That way that we do this is when we compare or make a comparison to this right side, we just had the value of 4 times x plus twice the value of y. And what we know is that this value right here, or excuse me, these values over here represent twice as many of these here. And by dividing out that 2, cutting this side in half and cutting this side in half, each of the terms, we're left with that x plus 3y is equal to twice the value of x plus that 1y. And so it might look a little bit funny based on here. What it tells us is that these x's have some significant value that affects the y as well. And we've really just divided this side in half. And now, check this out, we've divided this side in half by taking off a y and taking off 2 of the x's. So maybe a little confusing, may not have seen that before, but that's division of common values on each side, or what we call the division property of equality. Finally, the last thing that we're after with this, since there's no more dividing out groups, so on and so forth, or we could do the same thing, but not really because there's not a factor of 2 of these x's in there. What we would be doing on this last part is eliminating x's and y's. In this case, I can eliminate from here. I can eliminate 1x from this side right here. I can eliminate an x from this side over here. I can eliminate a y and a y, leaving me, by the time I'm done with all of this, twice the value of y is equal to just a single x. Hopefully that makes some sense to you. What I mean by that is eliminating a y and then eliminating an x. And then we see that we have twice the value of y and just an x for the final sequence here. Okay, quite a bit there. I know it's a little bit different looking at it. Let's look at what we see. Each variable, x, y, and z, represent the weight of one shape. Which one goes with which? We saw that the square is equal to x. the triangle was equal to y, and the circle was equal to z. Now explain what was done to each equation to create the next equation. If you get stuck, think about how the hangers changed. What we used in this is what we call inverse operations. That's what's going to be coming as we're taking inverse operations as well as properties of equality is what our more appropriate term is. And what we mean by properties of equality is that we are keeping each expression equal to each other so that the equation can still be considered an equation. Those properties of equality meant that by removing certain amounts, in this case right here, we subtracted 2z from each side, from each expression. In B, we divided each expression by 2. And then from C, we subtracted an x from this side and an x from this side and a y from this side and a y from this side. And then it simplified down. You'll notice that we kept the equality by removing or changing those values by the exact same value on either expression, maintaining equality. We'll get more into that as we get going. But that's essentially what we did. From A, we removed the z's. From B, from A, we did minus 2z. B, we did divided by 2. C, we did, let's look back, subtract x and subtract y. And from D, we just simplified. Okay. All right, we're going to skip over 3, 2, because obviously we can't do anything with partners right now. And now we're going to look at a comparison. Noah and Lynn both solved the equation 14 times A is equal to twice the value of the difference of A and 3. I think, yeah, it shows both of them right here. Do you agree with either of them and why? Let's take a look at what they did and see if we can follow how it worked out. In Noah's solution, what we see is that we start out with the original equation in both of them. But in Noah, his second step, he's got this part right here that says twice the value of A minus 6. The way that we found that, or that he found that, is he went 2 times A and 2 times minus 3. This is what we call the distributive property. Commonly, you'll be taught with people showing you an arrow across the top or showing you a line that connects the coefficient 2 to each of the terms inside of the parentheses. As next step, we see that the A is now eliminated, so he must have subtracted that 2A from the expression on the right, and then had to subtract that 2A from this expression on the left to maintain equality. We call that subtraction property of equality. And that leaves him with 14A, take away 2A is 12 times A. And then by taking away the 2A on the right, that eliminates it, making this just a minus 6. The final step, we have multiplication, 12 times A. And to undo that multiplication, or the inverse, would be to divide by 12 on both expressions. And using that as the division property of equality. And we're just left with a single A, and negative 6 divided by 12 is the same as negative 1/2. That's awesome. Noah solved correctly. Here's what Lynn did. Lynn solved by saying she went from 14A, and in her very next step, she went to 7A. The expression on the right went from twice the value of A minus 3 down to A minus 3. So what we see is this 2 is gone, but how did it go away? From this side, it's gone, but over here, we know that 7 is half of 14. So Lynn must have just divided by 2 straight away to change this side. 2 divided by 2 is 1, thus making A minus 3 because of the multiplication property, or excuse me, the identity property of multiplication. 1 times anything equals itself, just leaving this as one group. 14 divided by 2 is 7 times A. And from here, our next step was to subtract the A from the expression on the right and the left to eliminate it from this expression. And to change this expression, it would change it to 6 times A. followed by the same last step, multiplication property of equality, and -3 divided by 6 is a -1/2. So we actually see that both Noah and Lynn are correct. They just went through different methods to solve. They both followed all the rules. They both did exactly what they were supposed to do. So what you're going to find with this as we solve equations is that there's multiple approaches to this as long as you're following the rules. Think about it in a game. If you don't follow the rules, you either get in trouble or you forfeit or something else. You get the steps wrong. So let's look at this one with Elena. Now we don't have hangers. We don't have anything else. We're just going to look at this equation and see what can be done. So Elena is asked to solve 15 minus 10 times x is equal to 5 times the sum of x and 9. What do you recommend she does first on each side? Like I said, she has a couple of different options that she can use here. The first option that most people will think of, or that most of the time that we see, is the distributive property, which means I'm going to take 5 of these groups. Think in mind what this means. This means 5 of x plus 9. That means x plus 9 times x plus, or plus x plus 9, plus x plus 9, plus x plus 9, 5 times. 5 of those groups. A simpler way to look at that is just saying, after you're all done, is, well, I have 5 x's and then I have 5 9's, which means that I have 45 altogether for my constant, and then I have 15 minus 10x. The way that I would see that from up above here is I would see 5 times x plus 5 times 9. Optionally, she could go like this and eliminate that 5 off of the expression on the right first, because it's multiplying this group by this group. So if I make this expression 5 times smaller, and I make this expression 5 times smaller, then you might notice that I wrote the 5 underneath the 15 and the 10. It's because these two terms are separate in this expression, and the 5 and the x plus 9 are two separate terms. This is a term all by itself because it's all by it, or it's grouped up in the parentheses. So when I divide this, you might see sometimes people write it like this, where they just put a 5. I find it helpful with a 5 under both of them, so I don't forget to do one of them. But either way, 15 divided by 5 is 3. Minus 10x is a minus 2x is equal to an x plus 9. We see that this is eliminated because it becomes a 1. And we know that both of these equations are the exact same, and they will ultimately give us the exact same outcome. Now, if we look at the next one, number 3, Diego is asked to solve this equation. What do you recommend he does in this to each side first? I'm going to look at this part right here and see if division would work. 8 divided by 4 would be 2, but 3 divided by 4 would be a fraction of 3/4. This is not ideal for what I want to do because the fractions are a little bit tougher. It is a possible outcome. So to avoid that fraction, I recommend first step is distribute. Um, 4 2x plus 5. And the reason for the distributive property is this. If I take the 3 times the x minus 8 is equal to 4 times x and 4 times 5, I can avoid having a fraction in there such as 3/4 x minus 2 is equal to x plus 5. You can see the difference between the two. Now I'll have to figure out how to work with a fraction, whereas over here I do not have to do that. Okay? All right. A lot of little things that I brought in there and a lot of new steps. I'm hoping that this is following, but then you recognize what's going on in each of these steps. The idea with this lesson is that we're able to start simplifying what we see. So an equation tells us that two expressions have equal values. The expression on the left, the expression on the right. That's the difference between an expression and an equation. An expression is just simply an expressed value. It becomes an equation when you compare it to another expression stating that type of relationship, in this case, an equal sign. Other comparisons that you might see are less than or greater than, less than or equal to, greater than or equal to, not equal to. These are all ways that we can compare expressions. Right now, we're focused on equations, focusing on the fact that the expression on the left and the expression on the right maintain an equal value. And that's the most important thing when we're looking at this. Little bit of a fun step to go with right here. In a cryptarithmetic puzzle, the digits 0 through 9 are represented with letters of the alphabet. Use your understanding of addition to find which digits go with the letters A, B, E, G, H, L, N, and R. Go ahead and give it a shot. See what you can come up with. See if you can make it work. This one is kind of fun. It is a good puzzle. It'll take a little bit of time. Don't do it until after your homework. So wrapping things up with the lesson. Equation tells us the two expressions have equal value. Expression on the left is equal to the expression on the right, which means 4 times x plus 9, and negative 2 times x plus minus 3 have an equal value and can be written as shown. Earlier, we used the hangers to understand that if we add the same positive numbers to each side of the equation, the sides will still have the same equal value. It also works with the negative numbers, meaning when we take away a value, we can recognize that those values also eliminate something. So when we look at this side, if we had that same value at the very beginning, 4 times x plus 9 is equal to a negative 2 times x minus 3. What we did here to eliminate this positive 9 is we added a negative 9, or the additive inverse is what that's called. And to eliminate that, because 9 plus a negative 9 is 0. But we can't forget to do the exact same thing over here on the right side because of equality. We have to maintain that property of equality by adding the same value to the other side, which means that we end up with 4x all by itself here on the left. The minus 2x hasn't changed yet either. And then we have a minus 3x, or minus 3 plus a minus 9, which gives us a minus 12. Our next step that we would do, you'll see it on the next page, is that we would have to add the 2 times x and the 2 times x to both sides. We can call this the addition property. Of equality, which would leave us with a simplified version. 2 times x is equal to a minus 12. Or we combine like terms as our next step. And then our final step is to use the division property of equality to reveal that x is equal to negative 6. That would be called our solution. So this is combined like terms, division property of equality, and then solution. All right. We'll get more into these steps and more in depth to that, but this is your evidence for a claim that you're making over here. Just a slight little difference for what we talked about here on this one. Since expressions represent numbers, we can also add expressions to each side. So when we're talking about on this one, we have 4 times x plus 2 times x is equal to a negative 2x minus 12 plus 2x. This is that step that I showed where we would add the 2x to the expression to eliminate these two. Whoops, sorry, not eliminate that one because that's eliminated when we combine like terms. They did not use the same terminology here as I did, but the terminology over there is something that you're going to see again soon. The next step that they looked at was a little bit different. We were seeing this piece about multiplying by 1/6. Multiplying by 1/6 is the same thing as what I did with dividing by 6. You'll notice that you see both pieces right here. If we can learn that multiplying by the reciprocal will eliminate a coefficient, it will always work for us. So there again, I will go back to this and say these moves are systematic ways to solve equations. There's a lot of different moves that you can take. There are different approaches that you can take, but in the end, we get one single answer most of the time. There's a couple other ones that we see called no solution and then infinite solutions. We will get to those later, but for right now, we need to understand that we need those inverse operations. We need to keep the equations equal by removing or adding values from both expressions to make sure that equality stays there. Let me know if you have any questions. You're doing great. Give it your best bet. We'll see you in the homework.